First, let me apologize for canceling class today. I know that was weird and unusual, but as Megan and Alex, I'm sure, can tell you, linear today was a disaster. So and then trig was equally as much of a disaster trying at 10 o'clock. I have no idea what was going on with the internet today. It was not fun. So we will try it this way. This time we'll do a little bit of a lecture this way. Hopefully this goes okay. I'm just going to focus on what I would have covered today for the problems that we needed to finish up from section 8.5. You already have a video that I asked you to watch for sufficient statistics. That's over section 10.1. If you've already watched it, great. I would suggest perhaps maybe looking over it again, just making sure that you've got the kind of ideas that we're talking about down in that particular video. If you have not watched it yet, I would encourage you to watch it because it may be the case that we may just have to be doing lectures this way with me recording and uploading videos if Zoom is going to be the complete and utter jerk that it was this morning. So I've got a contingency plan for Monday. I really want to lecture for you guys because I think you're going to be asking questions about these things like I mentioned in the video for 10.1. This material is more difficult. So the new material is going to be more difficult. It's more conceptual. It's not going to be showing you things on Excel. I'd really rather you have the ability to ask me questions. So I've got a contingency plan. It's a little weird, but we'll see if it works. I hope if the video doesn't work for the computer using my hotspot doesn't work, this contingency plan that I have will. We will see. I'm not going to hold my breath on it, but I do have a backup plan, and if that doesn't work, then we're just going to have to go to I will lecture on video and you will have to ask me questions and I'll just be available during our usual class time. That's not at all how I want to do this, but it may be the only option that we have. So that enough of a preamble. Let's go ahead and talk about these last couple of examples. Okay, so we've talked about the Wilcoxon sign test when we've done, let's just recap because we've done a few of these. Okay, if it'll actually open. We've done ones where we've just had a single set of data where we wanted to test whether or not the median was, in this case, greater than 1.14. And that was when we did the signed ranks of things. And we said that when we do that statistic and do the sum of the signed ranks, the mean's always 0. Have that specific formula for the variance. This was another one just like that, but we also compared it against 2 other tests that we've had and said, hey, by the way, what do we notice about the different tests that we did? Remember, the sign test does not take into account the magnitude that a data value is away from the purported median. So for this example, even though I don't have the work here, remember we did not reject here. However, when we took into account the magnitudes, we were able to reject at the 0.05 level for part B. And then the t-test had that assumption that the underlying distribution was normal. And with that underlying distribution being normal, we actually even got a little bit better p-value than we had with the Wilcoxon sign test. Okay, so that was the comparison we did there. And then in the other problem, we had 2 different sets of data, but they were paired. So the first thing is that we did was subtract them from each other and then do the Wilcoxon signed rank test on the differences. So really wasn't anything new. We just had to do a subtraction first. But again, the important part in this particular example was the data were paired to start with, so the subtraction across made sense. In these last 2 examples, we're being asked to make a test of the medians of 2 different populations that are not paired. This one specifically says that we're doing failure types of a certain type of light bulb produced by 2 different manufacturers. So this 5.6 and this 7.2 don't have anything to do with each other except that they randomly selected this light bulb first, said it had a 5.6 hours of use before failure, and this one had 7.2, and it just happened to be picked first. There's no connection between these 2 data points, so there is no sense in trying to subtract them to pair. Okay, so don't do the subtraction here at all to start this. You don't want to do that. So we're still going to do a Wilcoxon sign test, but we're going to do it a little bit differently because we're not going to rank them by their signs. We're going to rank them if we stuck them all in order and then try to figure out if these, on a relative sense, are mixed in throughout the whole distribution of ranks or if they are piled at one end versus another. And I'll tell you what I mean by piled here in a second. But regardless, the first thing we're going to do is we're going to get the ranks of these data values all together. Okay, so rank average of this value relative to the whole thing, and make sure that's absolute cell reference. And again, we want ascending order so that the smaller things are ranked lower. Okay. So I'm going to rank each individual data point like I've glopped them into one big sample. Okay, so I'm not treating them as two separate samples right now, just one sample by itself. Okay, so I will copy this over to column E and copy it down. All right, so notice that I put all of the X's in the first column, all of the Y's in the second column. That was purposeful because it makes it easier to read this thing. I would encourage you to do that on any of these problems that you need to do. Make sure you put all of the one population that you've got the sample for in one column and then all of the second population in a second column, or at least keep them separate. Don't actually mix them together because the way we're going to calculate the statistic is going to be based on one of the distributions, okay? Not both. All right. So before we do any of these calculations, we notice that it looks like, just by looking at these ranks, doesn't it look like the values for Y are, on a relative sense, bigger than the values for X? Look at these ranks. They're all much larger than the ranks over here at their X counterpoint parts. All right, so here's how the Wilcoxon rank test works on comparing two populations. Okay, so the first thing we're going to do is we're going to add up all of these, all of the ranks that are associated with the, all of the ranks that are associated with just the Y in this case. So we'll do the sum of those things here. All right, so those are the sum of those ranks. So this is our new W statistic. So we're not signing anything here. We're just adding up the values that correspond to the Y's with those ranks. Okay, so I didn't write this down. I probably should write this down. So the null hypothesis that we're testing here is that the median for X is equal to the median for Y. And this is looking at the data, by the way. This is, they didn't tell us what to test it against. Okay, it just said test the equality of means or failure of means. But looking at this data, I'm going to say we're going to test the median for X is less than the median for Y. Okay. Get rid of that space in there because it's bugging me. Okay. All right, so all we did for this W statistic again is the sum of the Y values only, not the overall sum. Okay, that's how we got this W statistic. The reason, again, I could have done the sum of the X values only. It would have been similar. Okay, doesn't really matter. It's just one of them is going to give you a positive answer here in a minute, and the other one's going to give you a negative answer. And we can actually check that, and we should get the same conclusion one way or the other. All right, so let's talk about what we need to do with this distribution of W. We're not going to actually compute the distribution of W. If you look at the top of page 449, it says, we shall not derive the distribution of W. Okay. The reason it's not an easy distribution to derive. So what we're saying here again is that if the medians of these two things were supposed to be equal to each other, then we would expect that the distribution functions should have, well, essentially relatively the same, but they should have relatively the same shape. But the distributions of these things, for as far as the ranks goes, should be more mixed up than this. There should be some low values and some high values here in the X's, and there should be some low values and high values here in the Y, because again, we're thinking it's a 50-50 shot to pick a value below the median and above the median, right? So if the median for both of them are the same, then they should be kind of spread out the same here across the medians. We wouldn't expect to see a bunch of big ranks on the y's and low ranks on the x's. Okay. All right. So anyway, so that's what we're basically testing, is if these distributions are the same. Now, if they are the same, assuming that the medians are the same and the distributions are the same, then the mean of the W is, and the formulas here are on page 449, by the way, if you want to look on your book, 449. The mean of W is going to be what they refer to as N2 times N1 plus N2 plus 1 all over 2. Let me move this over so it's not in where I want it, in the way. All right. Okay, so I need to tell you what N1 and N2 are. So N1 is the number of x's, and N2 is the number of y's. Okay. Now, it's important that when we're doing, notice that we add, with this W, we added up this. This was our Y, right? So I'm using the N2 here. Now, in this case, they're both the same, so it wouldn't be a big deal. But if you had different size data sets, it matters what the N2 is out here in front. So I added up the Y's here. So I'm using the number of Y's on the outside. If instead we added up the X's, we would put the number of X's on the outside. Okay, just to keep that straight. All right, so this N2 is referring to how many things were in the Y sample. We're going to do one here in a minute where they don't have the same number of elements in the sample. All right, variance of W is going to be N1 times N2 times N1 plus N2 plus 1, all divided by 12. So now this one, it doesn't matter which one is N1 and which one's N2, because it's symmetric. If I flip the numbers around, I'm going to get the same answer. But it matters for the mean. Whatever ranks you added up, that's the number of things that you want out in front of this product. All right, so now we're going to use the normal approximation for this particular, this particular statistic, this particular random variable. It turns out that as long as your N1 and your N2 are both bigger than 7, then the normal approximation is pretty good. I don't have a nice fancy picture like I did for the Wilcoxon test, the side rank test itself, but that's okay. All right, so in this particular case, let's do the test statistic. So we will do 145, well, I'll just go click on it. 145 minus the mean. Well, how many elements are in here? It's 10 light bulbs, so it's 10 times 10 plus 10 plus 1. 21 over 2. And then I have to divide that by, no I don't. I don't have to divide by, oh yeah, I do. I need to divide by its standard deviation. So I have to divide by the square root of 10 times 10, because that's N1 and N2, and then times 21 again over 2, over 12, not 2, 12. Okay, so what am I doing here again? We're using the normal approximation. That's not test stat, this is z-score. Let me go back to that, sorry. This was your test statistic. This is your z-score. What are we doing? Data point, 145, minus mean. Where did I get these numbers? N2 is 10. That was the number of y's. 21 is 10 plus 10 plus 1, all over 2. Where did I get this number? Remember, it's data point minus mean over the standard deviation. This is the variance, so I have to do square root. N1 and N2 are both 10. N1 plus N2 plus 1 is 21, all over 12. That's where I got that. With a z-score like 3.024, we certainly reject here, without a doubt. Okay. Now this one, unlike what we said for the Wilcoxon sign rank statistic, where we had to do a full unit continuity correction for a p-value, the reason we had to do the full unit possibility was because we had odds or evens. We didn't have anything in the middle, so we wanted to cross a whole 2 units instead of 1. So this can be anything, because these ranks can be odd or even. So we're going to go back to the half unit correction. I know. I can hear you all complaining about doing the half unit as opposed to the full unit correction. But this one we can do a half unit correction again because we don't have that 2 unit span of the bases of our rectangles. Okay. So we're going to have it half unit correction. I don't know why I typed value. Okay. All right. So here I want the probability that W is greater than 144.5. That's our half unit correction, right? A half unit below because we got a right tail that we're doing here. So let me calculate. Let me grab this formula. Okay, I'm going to grab that formula. I want to do 1 minus the normal distribution on that z. Actually, I can do norm.s here, dot distribution, on that z-score, except that I want to subtract off 0.5, doing that half unit correction. Okay? Everything else is exactly the same. I'm just correcting that by a half a unit. So I'm doing the 145 minus a half, and then minus the mean, and then divide by the standard deviation. And then I want cumulative here, so true. Okay? So all I did was I went back up to my z-score, I copied the formula, and just put it in the standard normal distribution here, and then subtracted off the 0.5 from the test statistic. And we're going to do another one here in a minute, so hopefully you'll see what I'm talking about at that point too. So our p-value is really, really, really small. We expect that here, right? We expect it to be small since that z-score is above 3. That's not a very likely z-score. So we would conclude here, the conclusion, we're going to reject the null hypothesis and conclude that the median for the y's is greater than the median for x's. So the second manufacturer produces a better light bulb, or at least a longer lasting light bulb. Maybe it doesn't burn as bright or something, and that's why it lasts longer. All right. I would ask if there are any questions, but I'm not going to hear anybody say anything. So if you have questions, make sure you holler at me later. All right, let's do this one. Same concept. We want to know, is the median for the 48 passenger buses, which is this list, is greater than the median for the 38 passenger buses for this one. Now I'm going to focus on the second one as my y again, but it really doesn't matter which one's x and which one's y, as long as you make sure that you count that n2 in your mean formula as the one that's the mean for the ranks that you're adding up for the second population. All right, so first thing we're going to do, get our ranks. Okay, so let's rank this one relative to the rest of the set. Make it absolute cell reference. That's important. Oh, and one more thing that's important. Make sure it's ascending order. Okay. And now, copy that over and pull it down. These two are not applicable, so I'm going to delete them out. All right. Well, looking at the ranks themselves, again, we're trying to see if the mean for the 48 passenger buses is greater than the median for the 48 passenger buses is greater than the median for the 38 passenger buses. Well, I see mostly big ranks over here, but I see some big ranks over here too, so I'm not getting a feel from just looking at the ranks whether or not this should be true. All right. So let's calculate our test statistic. I'm going to calculate it on the second one again. Even though it says the 48 bigger than the 38, I'm going to calculate it on the 38. So that's the same as the 38 being less than the 48. All right, so this is just the sum of the ranks. This gives me 108. All right. Let's just calculate the mean and the variance of the ranks separately. So just so that we remember the formulas. So this is going to be the mean of W, and this is the variance of W. That was interesting. Thought I typed in a W there. Okay. All right, so remember the mean of W here is, it's the number of Y's, and I'm using this as my Y's. So there are, how many here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? It even tells us sample size 11. All right, so 11 is my N2. So then it's N1, which is 9, plus N2, which is 11, so that's 20, plus 1 is 21, and then divided by 2. So that's the mean of W here. The variance is N1, 9, oops, 9, N2, 11, N1 plus N2 plus 1, 21, over 12. So now I have the mean and the variance. So now I want a z-score. Data point, 108, minus the mean, 115.5, divided by the square root of the variance. Boom. All right. That z-score is relatively small, right? And it's also negative, which makes sense because remember, it said test whether the median for 48 is greater than the median for 38, or flipped around, the 38 is less than the 48, which would mean that we would expect a z-score to be negative in that case. So not a huge surprise that we get a negative there. We are definitely not going to reject. There's not going to be any significance level that you're going to use that says reject H naught, and certainly not at the 0.05 level. P-value. Remember what we want to do. In this case, we want to, it's a left tail test because we got a negative z-score, definitely. So I just need to do the normal distribution before I do that. Let me go back up here and grab the formula that I used. All right, I want the normal distribution, normal standard distribution here. I'm going to take our data point, which was at E26, but I'm going to add 0.5 in this case. Half unit correction again, remember, because we can get evens or odds for when we add these up. So there's not that 2 unit interval span for possibilities. So half unit correction again. I'm adding in this case instead of subtracting because I need to catch 108 down to the left tail. So I have to go a little bit above it. So I need that 108.5 here. That's why I'm adding. Okay, so 108 plus 0.5, so 108.5 minus the mean divided by the standard deviation. And just like before, we want cumulative. And so our p-value is really high at about 0.3. All right, so again, this tells us that we do not reject H naught. And just to remember, just to point out one more time, this is use half unit correction for this one. All right. So this was the last thing I needed to talk about before be able to complete your homework problems. Just like before, you should be doing everything in your homework on Excel. I don't think there's anything on there that's not on Excel. And you should use the data file that I put on Excel for you so that you don't have to worry about typing them all in for yourself. So anyway, I'm going to stop there. Like I said, if you have not already, watch the sufficient statistics video that I posted on YouTube. If you have already watched it, you might want to go back and rewatch it before we talk on Monday. That stuff, again, like I mentioned before, the stuff at the end here is, it's heady stuff. It's really conceptual. So That's why I really want to hopefully can get the live stuff working, because if you've got questions as we go, I want to make sure that I'm able to answer those questions. But if not, we may just have to do this asynchronous me lecture, post video, me available for questions. Not ideal, but it just may be the way we have to go. But anyway, everybody have a great weekend, and I will hopefully we'll talk to you on Monday.